Great. So I'm going to be talking about signaling. And by way of introduction, so this is going to be somewhat different from the lectures that you've seen so far. I want you to sort of think about, you've probably all seen signaling games of some sort, like Spences and so on. I want you to think about this sort of in the context of the series as just being canonical applications of dynamic games. Okay, so these are, what I'm going to be talking about are very simple dynamic games. The key thing is going to be that there's asymmetric information. Okay. And in general, in costly signaling games, there's lots of kinds of signaling games. I'll talk about some other kinds in the second lecture, but for the first lecture, I want you to think about costly signaling games in which there's going to be an informed agent who's going to be taking some kind of a costly action in order to affect an uninformed agent or market's beliefs about the agent's type. Okay? The general question that one is interested in when thinking about signaling games, or at least one question that one is interested in, is how much information is revealed by the agent's costly action about her type. Okay? So if you think about standard models, like Spence's education signaling problem, there's a very simple answer for the following reason. So one typically thinks about there being some set of types that's ordered from low to high. Okay? And the agent wants the market or uninformed observer to perceive her as being a high type, okay, a more able worker in Spence. And then one makes an assumption about the signaling technology that's generating some kind of a single crossing property. Okay, so specifically in the Spence context, one assumes that higher types have lower marginal costs of acquiring more education. Okay, that generates a single crossing condition that's sometimes referred to as the Spence-Merlis condition, and this produces the existence of a separating equilibrium. Okay, and so what is a separating equilibrium? It's an equilibrium in which the agent's action is going to fully reveal the agent's type. Specifically, again, in the education context, you're going to have more able workers choosing more amounts of education. Okay. So observe, even though the market doesn't directly observe the worker's ability, observing the education choice allows the market to invert and figure out the worker's ability. And one thing that's particularly striking about that problem is that the amount of information that's revealed to the market doesn't vary with lots of parameters that you might think economically do matter. Okay, so for example, how much the agent cares about affecting the market's belief relative to the cost of acquiring education doesn't affect the existence of the separating equilibrium. Okay, I'll make that more precise if it isn't already clear in a little bit. Say that again.
It affects the equilibrium.
It affects the equilibrium, but it doesn't affect the amount of information in the equilibrium. So the fact that the separating equilibrium exists doesn't vary with things like how much the agent cares about affecting the market's belief. It's going to affect how much education is actually acquired, and in that sense affects the equilibrium, but it doesn't affect the informational content of the equilibrium. Okay, so this sort of, if you think about many applications, I'll give you a couple of examples to motivate stuff in a second, but it's not hard to sort of think about applications in which two things are true. One of them is that people aren't separating. Okay, so the amount of information that's revealed is imperfect. Okay, and secondly, sort of somewhat even more importantly, there's a concern that the agent's desire to signal actually reduces market information. Okay, so this is referred to in sort of popular language as gaming. Okay. And this is sort of, again, it's antithetical to what you think of in a standard signaling model, okay? Because if you think about Spence, if agents didn't care about affecting the market belief about their ability, you would have no information revealed to the market. It's precisely the fact that agents care about affecting the market beliefs that leads to the generation of information in equilibrium, okay? So what I want to talk to you about today is a family of models, okay, in which the agents are going to vary on multiple dimensions. So it's going to be multidimensional signaling. Okay? And the relatively unsurprising part of this is that quite naturally, under natural assumptions, the information that the market gets about one dimension of an agent's type is going to be muddled with information about another dimension. Okay, so that's the muddled information part. And in general, one won't get full separation here. Okay, and then the real sort of theoretical heart is sort of trying to understand when and how is it that greater desire to signal either improves or degrades the amount of information revealed in equilibrium. Okay, so that's sort of where I'm headed. So just a couple of applications to have in the back of your mind to sort of think about the model and think about the analysis. Okay, so one of them, I mean, this is framed in the U.S. context, but obviously this applies to probably most parts of the world. So think about college admissions for a second. In the U.S., students take this SAT test, which is one key component of their college admissions decision. And the SAT test, the score that you get in the test, is supposed to be viewed as a signal of your college aptitude. Okay. Students can engage in various kinds of test prep in order to improve their SAT score. Okay. And the key thing is that even conditional upon a student's natural ability or intrinsic college aptitude, whatever you want to call it, some students are going to be better at preparing specifically for the SAT than others. For example, this might be because you're wealthier, and so you can afford to just get more tutoring or take sort of get more test practice that are graded carefully and so on. Okay, so the idea that people talk about in both academic and popular writing is sort of that the score, the SAT score, muddles two things. One is intrinsic college aptitude, and the other is your ability to engage in test prep. Okay, so that's the sense in which there's going to be muddling in this example. Here's another one. So if you think about web search, okay, so when you type in a keyword into Google, you get a list of hits, okay, that Google suggests for you, and I'm talking about the kind of the white part of Google, not the yellow part, not the sponsored search part. Okay, so there's something that's referred to as search engine optimization, SEO. And sites can engage in this in order to rank higher, okay, on the list that Google spits out for each keyword, and it's a pretty big industry. Okay, so some sites are either more interested in using or just have higher resources, they have better workers, etc., to engage in this kind of SEO. And so Google's ranking is going to muddle two things. One is sort of the intrinsic relevance for the keyword that the user has entered, with the site's skill at search engine optimization. Okay, and this is again a concern that Google actively tries to deal with, and I'm sort of happy to talk more about that if anyone's interested, but it should be fairly clear what the muddling over here is. And so these kind of examples motivate thinking about the following kind of a model. So here's just an overview of where I'm going, and then I'll jump into the formalism. Okay. So the model I want to talk about is going to have multiple dimensions that affect an agent's cost of signaling. Okay, so there's going to be one dimension that I'm going to call the natural action. Okay, and you should think of this as sort of the intrinsic ideal point, or the action that the agent would take in the absence of any direct signaling concerns. Okay, if they didn't really try to affect the market's belief about their type, what is the signal that they would generate? Okay, so in the context of the SAT, this would be if you didn't study specifically for the SAT, what is the score you would get by taking the SAT? Okay, and there's going to be heterogeneity naturally on that. And the other dimension is going to be something that you can think of as either gaming ability, which would be sort of what is your skill at increasing your signal above the natural level. So how much are you willing to pay in order to improve your SAT score? Okay, or you can think of this, it's going to be isomorphic in a certain sense. This can also be viewed as just your private signaling benefit. You know, how much do you care about affecting the market's belief about your type? Okay, so each dimension is going to be ordered by single crossing. Okay, and so this means that sort of if you have a higher type on either dimension, you're going to have either a lower marginal cost or a higher marginal benefit of taking higher actions. Okay, so if you had homogeneity in one dimension and heterogeneity in the other, you're essentially back in standard models. Okay, so the key thing is going to be the interaction of the two, and in particular, there's going to be no global single crossing condition. Okay, because there's generally going to be, depending on what the type space is, but in natural type spaces, there's going to be cross types. And what I mean by cross types is sort of someone who's high on one dimension and low on the other, compared to somebody else who's low on the first and high on the second. Okay. And there's going to be an assumption about the relationship of signaling costs for these cross types that's not specified by just this assumption. Okay. And so we'll dig into that. And then the results that we're going to be after are the following. So we're going to generally think about there being one dimension of interest, which is the market sort of cares about evaluating the agent on one of these two dimensions. Either the market wants to evaluate the natural action or the natural ability. That's probably the more salient case if you think about applications. But you could think about applications in which we care about figuring out what an agent's gaming ability is. Okay. And so, as I said, in equilibrium, information is going to be muddled about the dimension of interest with the other dimension. Okay, so higher actions are going to be correlated with higher types, but imperfectly so. So you see, let's say, an intermediate action is the market. You don't know whether it's coming from an agent who's high on the first, low on the second, low on the second, low on the first, high on the second, or perhaps just middle on both. Okay. It doesn't have to be. So if you like for intuition, think of it as being independent, but you can allow for various kinds of correlation. Okay. Yep. Mm-hmm.
So you can order these things right in the two dimensions if both are high or low.
Yep.
And what is in the other case? You have a way to order them also?
Yeah. So the key thing is going to be. Is there chalk somewhere? Ah, yes. Thanks. Can you see that? Yep. Okay, so suppose here we have the natural action, and here we have, it's going to be gamma, the gaming ability. Okay. So the key thing is going to be, if you have types that are here and here, so high, high, low, low, that's going to be ordered. Okay. You'll be able to, if you only had this kind of a type space, then you would just have a standard separating equilibrium. The key issue is going to be, what about types that are like this? So they're going to be in between, in a certain sense, between this type and this type, but they're not going to be ordered across each other. Okay, and so there's going to be an assumption that one has to make about the relationship of signaling costs for these two types that's going to generate certain comparative statics results. And let me hold off on that until I give you the formalism.
Supposing that is invertible, you get these observations, and then you go back. Suppose you can reconstruct the determined the matrix of mapping this on the things you really want.
Yep.
Is invertible.
Mm-hmm.
Determined, it never vanishes. Does that matter?
So
generalization of the single crossing division.
Yeah, so one could, right, so the key thing is that it's going to be that in equilibrium, the mapping from these types into the equilibrium actions is not going to be invertible.
It's not.
It's not going to be invertible.
It could be.
Right, so it could be. So for example, if I just excluded these types and just said that the type space consists of just these two types, then it would be invertible, or at least there would exist one equilibrium in which it's invertible. Yeah. So again, I'm still just being just giving you motivation yet. So once I give you the formalism, maybe it'll help. Okay. So the main thing that the main technical thing that I'm going to try and convey is a certain kind of comparative static. Okay. So the comparative static that we're going to be after is the following. If we raise the incentive to take higher actions, okay, in a certain sense, so this could be either because you sort of increase the stakes in signaling, people just care more about signaling relative to the costs, or you could think about this as making it easier to manipulate signals, which is effectively formally going to be like reducing costs, okay, then this will tend to increase the amount of gaming or the amount of distortion from the natural behavior, okay. And therefore, this will decrease the amount of information in equilibrium about natural actions, while at the same time increasing information about gaming ability. Okay? So depending on what the market cares about, it's either going to get more or less information when the parameters change. Okay, and then I don't think I'll have time, given we only have an hour and a half that I want to spend on this topic, but sort of there's a bunch of interesting applications that one can flesh out using these kind of results, okay? Yeah,
And
Eric.
you've been talking implicitly as though having more information is a good thing.
Mhm.
That what we want out of an equilibrium is to be able to separate types. But of course, it's costly to do that
Yep.
because the signaling activity, whatever it is,
Yep.
is not free, and in fact, it may be entirely wasteful.
Yep.
I think in Spence's original model, education didn't enhance productivity at all. It was just there to enable you to distinguish yourself from others.
I mean, so you...
You might actually want to have a pooling.
Yes, so it's certainly true. So one thing that I'm not going to talk about here, there's been some work on this, and I'm happy to talk about it, but it's sort of, one has to balance sort of informational content of equilibrium with the actual signaling costs. And for example, if you thought about the social value function over information as being linear, so that you really don't value, or sorry, let me rephrase that. If you thought about the social value function over beliefs as being linear, so that you don't actually value getting more information, then you'd certainly want to just have pooling and avoid any kind of signaling activity. Okay. On the other hand, even in the basic Spence model, even if it doesn't actually affect productivity, you might think that the social value function is convex because you want to match more able workers with certain kinds of jobs, and Spence talks about that.
Yes, that's right. I think in the simplest model, the payoff is a linear function of ability.
Yeah.
So you just pay the average wage and you maximize net output that way. But if there were different jobs and
Yep.
you wanted more able people
Yep.
in the more demanding jobs, then yes,
Yeah.
you'd want a signal for that purpose.
Yeah, so completely agree. So sort of the focus here is all going to be about information, setting aside the question about exactly what are the signaling costs that are being borne in order to generate that information. And if one wants to do sort of a net calculus, one would want to balance these two. Okay. Okay. So that's where I'm going. If there are no other questions, I'm going to jump into the details. Okay. Okay. So here's the model. There's an agent, or if you like, sort of there's a bunch of agents, sort of with a large number. You could think about it either way. And so the agent's going to have a type theta, okay, and it's useful to keep this notation in mind. So theta, think of this as mnemonic for type, and theta is two-dimensional. It's going to consist of a first component eta, which is supposed to look like an n for natural action, okay, and then gamma for g. It doesn't quite look like a G, well, I guess it sort of looks like a G. So it's gaming ability, okay? And just for technical reasons, this eta is going to be any real number, while gamma is going to be a strictly positive real number, okay? So this is going to be the agent's private information. It's drawn from some CDFF, which has some compact support cap theta, okay? So the agent's going to take a signaling action. Okay, so the agent's going to learn her type. Nature is going to draw the type. Agent's going to observe that, learn her type, and then going to choose a signaling action A, that's a real number, at some cost, capital C, which depends upon the action taken and the agent's type. Okay, and I'll either write it as just theta or depending explicitly on eta and gamma. Okay, so there's going to be a market or an uninformed observer, okay, who's going to be very passive. The only thing that this agent is really going to be doing is updating Web-based rule, nothing else. Okay, and so the market doesn't observe the agent's type directly, but does observe the action that the agent takes, and then forms a belief about the agent's type. Okay, and for much of what I have to say, we can talk about some other generalizations, but for most of the lecture, I'm just going to be thinking about this as the market is interested in one dimension of the agent's type. Okay, and I'm going to call that tau. It's either natural action or gaming ability. And specifically, it will be convenient to focus on the specification where the market just forms an expectation, tau hat, given the agent's action. Okay, so it forms an expectation of tau, which I'm going to call tau hat, after observing the agent's action. And that's going to be a sufficient statistic for the agent's preferences. Okay, so in the following way, the signaling benefit for the agent, if you like a value function v, is going to depend upon the market expectation, this tau hat, and some parameter s. Okay, and so for right now, this parameter s has no meaning. It's going to be useful when we want to do comparative statics. Okay, so one thing to note here is that the way I've written this may not be the way you saw this in your first year course. Okay, because I'm writing down the agent's value function directly in terms of the market belief. Okay, as opposed to, so if you think about Spence, what the agent really cares about is wage. The wage is going to be determined somehow through Bertrand competition or something else, okay, as a function about the market's beliefs. There might be two competing firms, etc. Okay, so there are a couple of ways to view this. Either you could view this as just being a reduced form, where what's happening in the subgame is just taken in a reduced form here, or if you like, you can even view this directly as a psychological game. And in fact, give you for example, this relates to some work by Benabou and Troll, where the agent may just directly care about the market belief, right? This is some image concerns, for instance. Okay, there was a question.
So how is known by the agent?
Yeah, so so I'll make this clear in a moment, but everything here except the agent's realization of private information is common knowledge. Okay, so all of these you should view sort of this cost function, which whether tau is eta or gamma, exactly what the value function is. These are all parameters of the problem. Okay, so in that sense, it's sort of just a standard signaling game. Okay, so this parameter S is going to be positive, and as I said, this is sort of going to be something that I'm going to use for comparative statics, and you should think of this, again, mnemonically as just being for the stakes in signaling. It's going to be a way to sort of parameterize how much the agent cares about signaling. Okay?
Can you explain a little more why only the expectation of tau matters?
Yeah, so this is a simplification. So in certain cases, so for instance, if eta and gamma could both only take two values, then it's isomorphic. The entire distribution can be summarized by the expectation. More generally, it's a simplification. So I can say some things about what happens when this is not the case, if the agent cares about some other statistic. You should think of this, for example, if the wage is being determined by just you have Bertrand competition and they're just going to pay you your expected productivity.
Well, it sounds kind of special. I mean, if this, for example, is the basis for employment, the employer might be interested in variance.
Yes, I agree. So just for now, take it as a simplification. We can talk a little bit about what happens in other cases. Okay. Okay, and so the net payoff for the agent is going to be the signaling benefit less the signaling cost. Okay. Okay, so in order to sort of do anything with this, one needs to make assumptions about what the signaling benefit. One needs to put some structure on what the signaling benefit looks like. Okay, beyond the fact that it just depends upon the expectation, and also something about the costs. Okay, so that's what we're going to do next. So here's the stuff about the signaling benefit. Okay, so these are assumptions on the V function. So it's continuous. It's strictly increasing in the market expectation on the dimension of interest. Okay, so again, if you want to, this is sort of analogous to a standard model. So if the market thinks that you have a higher natural action or a higher gaming ability, it benefits you either directly through psychological concerns or indirectly because of how it affects the wage more. Okay. So the second assumption here is increasing differences or supermodularity. Okay. So formally, you take any belief tau hat prime that's larger than tau hat. Okay, and again, these are the expectations. Then the difference in the signaling values evaluated at tau hat prime and tau hat is higher when the S parameter is higher. Okay, so another way of saying this is that when stakes increase, the agent benefits more marginally from generating higher beliefs. Okay, and this is what gives content to the interpretation of this S as being a stakes parameter. Okay, so when we increase S, the agent just benefits more from generating higher market beliefs, and in that sense cares more about signaling. Okay. Some of the results that I'm going to talk about are limiting results, and so I need some assumptions about limiting properties of this V function. And so what this says over here is that if you generate any higher market belief, okay, the marginal benefit of doing that, so the difference in the V's evaluated at a higher market belief and a lower market belief, tends to infinity as stakes blow up. Okay, so as stakes get really large, even small increases in market belief generate arbitrarily large marginal benefits to the agent. And the flip side, as stakes vanish, the gains from generating higher market belief vanish as well. Okay. And if you want to have an example in the back of your mind to sort of carry through, here's the simplest one could think of. So this value function capital V is just the stakes parameter S multiplied by some little v, which depends only on the market belief. Okay? And as long as that little v is strictly increasing, this is going to satisfy all these assumptions. Okay? And continuous, as long as the little v is continuous as well. Okay?
So this could be also S times T tilde just, it could be linear.
V could be linear. Okay? Could be concave, could be convex, as long as it's strictly increasing. Okay. Okay, so that was on the benefit side. So let me now talk about the cost side. Okay, so it's technical. So C is differentiable, and it's twice differentiable essentially everywhere. Okay, so except possibly at one point, and I'll talk about why except possibly at one point in a moment. Okay, that's just technical. And here's one assumption that's worth discussing a little bit. So we're going to assume that the cost of generating an action that's less than your natural action weakly is 0. Okay, so this is sort of, you should interpret this as the agent's ideal point, the kind of natural action that the agent would take in the absence of signaling concerns is going to be eta, and it's costless in order to generate lower signals, okay, lower actions. Again, if you want to think sort of, so we call those free downward deviations. You can think of this as, it's, you know, if without studying at all for the SAT you would get a score of 700, okay, it's easy to answer questions wrong and get a lower score. Okay, what's difficult is generating a higher score. Okay, so that's that. And then the second one here is standard, which is that the marginal cost is positive and increasing above the natural action. Okay, so the total cost function is convex. So that's derivatives there. So here's in pictorially, actions are here, costs are there. It's 0 up until your natural action, and then it's increasing on convex. Yes.
The second condition in order to prevent it, would you probably signal to the other side?
It's not critical. In fact, I'll talk about a variation of the model in which it's not true. Okay, there's some papers in the literature that look at a specification where this is not true. It turns out for some of the general results that I want to talk about, it'll be convenient. Okay, so I'll explain, for example, where we use that when we get there. Okay, so and then the next two assumptions are what I said about single crossing on each dimension. Okay, so when we're looking at actions above the natural action, the marginal cost of signaling is lower when you have a higher natural action. Okay, submodularity. Okay, so pictorially, again, actions in the horizontal, cost in the vertical, and if you take a type, I'm going to use lower bars for low and higher and upper bars for high. Okay, so if you take two types that have the same gaming ability, but one of them has a lower natural action and the other has a higher natural action, then the total cost curves look like this. Okay, that's what this assumption says. It's kind of the one with the higher gaming, higher natural action has a uniformly lower cost curve. Okay, and then the same thing on the gaming ability side. So if we're looking again at actions above the natural action, the marginal cost of signaling is lower when you have a higher gaming ability. Okay, so pictorially similar kind of depiction here. Fix the natural action. Take a type with a lower gaming ability, type with a higher gaming ability. The one with the higher gaming ability has a uniformly lower cost of signaling. Okay. Notice that these two pictures are not exactly the same. Okay, and it's important that they're not exactly the same. So The key thing is because of the free downward deviations assumption, when you have a higher natural action but the same gaming ability, you have a cost of 0 up until a higher point than the lower natural action type. If you just have a higher gaming ability, the cost is 0 up until the same point. It's then just that the slope is lower. Okay. Okay, and then here's the key assumption. Okay, so everything else up until so far should be relatively uncontroversial. So here's the key thing. So take any pair of what we call cross types. And so by cross types, I mean this. Okay, so take a type that has a higher natural action, lower gaming ability versus lower natural action, higher gaming ability. Okay. In order to get general comparative statics results, one needs to have some assumption about sort of the relationships of the signaling costs for these two types. Okay, and so here it is. So what is this saying? This is saying look at the ratio of the marginal cost of signaling. Okay, and written here where you've got the higher natural action divided by the lower natural action. Okay, so this ratio is assumed to be strictly increasing on the relevant region. Okay, because below the high natural action, this ratio is either undefined, if it's either 0 over 0 or just 0. Okay, so on the relevant region, it's strictly increasing, and moreover, it crosses 1 at some action, okay, that we're going to call the order reversing action. Okay, that's AOR. So again, it may be easier to think about this in a picture. So this is now cross types. So higher natural action and lower gaming ability than this type. Okay, so for the type with the higher natural action, the marginal cost starts out being lower than for the type with the lower natural action. Okay, and for both of them, these marginal costs are increasing. So both of them have convex costs. Okay, however, this is increasing faster than for the lower natural action type. Okay, and then eventually at this point, AOR, the slopes are the same. Okay, and then of course the ratio keeps increasing above that. Okay, that's what's being depicted here. So if you like, this is trying to capture the idea that when there's little amounts of distortion, little amounts of signaling going on, okay, what matters more for marginal costs is your natural abilities. Okay, when you have lots of distortion going on, what matters more for marginal costs is your gaming ability, your knowledge of the system, if you like, or sort of how well you're able to study for the test. That's what matters more when there's lots of distortion going on. That's what determines the which type has a higher marginal cost. Okay. Questions about that? So that's central.
So by distortions, you mean upward deviations?
Correct. So when you take actions that are above your natural action. I think it makes sense. You could go the other way. So
intuition could go the other way around.
yes. So when we talk, once we see the mechanism that's driving the results, we'll be able to then think about what happens in other cases as well. Okay. So
There's an intuition that you can gain in certain contexts. At least there's a limit to how much you can gain. At the end of the day, your natural ability.
yes. So you might say sort of if you want to be a world-class musician, then sort of at the end of the day, it doesn't matter how much you practice. If you don't have the innate ability, you just can't achieve extremely high scores on whatever the right musical test is. So
Infinity or finite level?
no. So the assumption is that it does. I mean, so these are twice differentiable functions, except possibly at some point. So the derivative is not actually going to be infinity at any finite point. Okay. So.
But this goes to infinity at a finite point.
Yes, so that would be one way of trying to capture what you're saying. And once we see the mechanism of exactly what the logic here is that's going to drive these results, you can easily then think about what would happen if you made alternative assumptions. Okay, so, okay, and that's basically it as far as the assumptions go. So then sort of the assumptions imply certain things. So here's one important point. Okay, so the previous assumptions imply that whenever you take a pair of cross types, there's going to be some other critical action, okay, besides the order reversing action that was assumed. There's going to be some other critical action that we're going to call the cost equalizing action, okay, ACE, that's higher than the order reversing action, and that's the point at which these total cost curves cross. Okay, so this was already evident in the picture that I had drawn. So not only is there the point at which the marginal costs are equal, so slopes are equal on this total cost curve, but the total cost curves are also going to cross at some point, and we're going to call that the cost equalizing action. Okay. So below the cost equalizing action, it's the type with the lower natural action that has a higher cost. At points above the cost equalizing action, it's the type with a lower gaming ability that has a lower total cost. Okay? Sorry, that has a higher total cost. Okay? So let me not go, because the proof is just computational. There's nothing really to the proof, right? You just write down what the difference in the cost functions is, write this as an integral, and then stare at this for a little bit, and in 3 minutes you'll see it. Okay. Okay. So just to summarize, here's sort of what the problem looks like if you had a very simple 2x2 problem. Okay. So here's a depiction. If we only had these 4 types, okay, this is what the total cost curves are going to look like. They're sort of the lowest type, the one with the low natural action, low gaming ability. This one sort of has just uniformly the highest cost curve. Okay. There's the highest type, which has a high natural action, high gaming ability. This has uniformly the lowest cost curve. Then there are these 2 intermediate types, that's what we were talking about earlier, where you have a high natural action, low gaming ability, or low natural action, high gaming ability. And these are in between in the sense of their cost curves, between the lowest and the highest. But these 2 are not ordered because the cost curves are going to cross at some point. Okay, so that's the picture. And if you want to again have some kind of a functional form in the back of your mind that's useful for applications, here's one family of them that's very tractable. Okay, so the cost over here is just so if this exponent is 2, for instance, and this is just quadratic in the distance between your action and your natural action divided by your gaming ability. Okay. Okay. So one comment before I jump into the analysis. There's sort of I'm going to talk about everything in terms of gaming ability and natural action, okay, because I think it makes sense for certain applications. But there's another way to interpret the problem that's also useful for other applications, which is, you know, if you look at a payoff specification that takes the following form: signaling benefit minus some little c function that depends only upon your action and your natural action divided by gaming ability, okay, like in the example I just mentioned before. Since this gamma is positive, this is obviously isomorphic to just multiplying through by gamma, so that you now have the benefit being gamma times v and a cost that depends only upon your natural action. Okay? And in this case, you can then interpret what I'm calling gaming ability just as well as being what are your benefits, your private benefits, if you like, from signaling. Okay? So this is the interpretation that's taken, for example, in some of Benabou and Troll's work, okay, where people may have different image concerns, and so the heterogeneity comes in there rather than on the cost side. Okay, but they're mathematically equivalent. Okay, so what are we going to be interested in studying here? So we fix the stakes parameter s, fix some type distribution f. Okay, this induces a signaling game in the obvious way. Okay. When I say that, you should stop me if it's not obvious. Okay. So there's nature's picking types, agents are privately observing their types, they're going to take the action, market's going to observe that, update, and agents' payoffs are defined in the way we specified. Okay, so that's a well-defined extensive form game. And so we're going to be interested in looking at perfect Bayesian equilibria here. If you like weak perfect Bayesian equilibria, so we don't have to, nothing's important is going to be happening with off-path stuff. So the market's going to form some beliefs tau hat. Okay, again, the expectation of tau given the action A. We require them to be Bayes consistent on the path. Okay, and then the agent is just going to solve this maximization problem. Taking as given what the market belief function is, he's going to choose the optimal action in order to maximize signaling benefit less cost. Okay, yes.
So the fact that tau is either beta or
Mm-hmm.
gamma, it's going to be like exogenous, right?
It's exogenous.
Okay, because could be, that's the thing it's not kind of clear, because could be the case that A still depends on my type, right, of data.
Mm-hmm.
So even in that case, he's only going to care about either eta or gamma?
Correct. So it's going to be critical that in equilibrium, typically, A will depend upon both eta and gamma. Okay? And the market will have beliefs about both eta and gamma after observing the action. Okay? The assumption is that the agent's benefit only depends upon the market's belief on one of those two dimensions. Even though the market will be updating, depends upon what the equilibrium looks like, but the market could be updating about both. Okay? So one can work out, at least in examples, specifications where the agent cares about some, for example, convex combination or some other way in which the agent cares about both components. Okay, so there's not just one dimension of interest, it's both. For the general results, it's more tractable with this specification, okay, where you only care about one or the other. And it's not unreasonable. Okay, so again, for example, if you're thinking about the SAT, what the agent is really, what the student is trying to convince the market about is that he just is innately more intelligent, or just intelligent may not be the right word. He sort of has innate higher college aptitude. Okay, or if you're thinking about the Google application, sort of you can think of this as websites are trying to convince Google that they're just a better match for the keyword that has been typed in. Okay, they're not trying to convince Google that they're better at figuring out how to stuff their web page with different keywords in order to sort of look better. Okay.
So basically, you want this to be unidimensional. I mean, it's for a technical reason. That's why.
Yeah. So you want, when I say this to be unidimensional, you want the value to only depend upon one dimension. The problem obviously is going to be inherently multidimensional.
Yes.
Okay. Okay, so now a couple of observations, and this will elucidate one place where free downward deviations is useful. Okay, so one observation is that a pooling equilibrium is always going to exist here. Okay, why is that? I have a compact type space. The free downward deviations assumption implies that we can always generate an equilibrium in which everybody just takes the lowest possible natural action. Okay. Because if you have a higher natural action, you can just costlessly go down to lower actions. Okay, and if we can support this equilibrium by saying that if you observe any other action, then the market just doesn't update its beliefs, for instance, or even more punishing beliefs. Okay, so if instead you had something like it was costly to deviate downward, then this argument doesn't work as simply anyway. The main gist of the results will not really change, but it introduces a bunch of complications that are not worth going into. Okay. Yes. So I don't want to talk much about refinements. Okay. In some specifications, refinements may be useful, okay, but not in all. So let me talk about that after the lecture if you're interested. Okay. So. Instead, what we're going to be after is trying to get what I view as being more robust comparative statics by sort of comparing sets of equilibria rather than comparing refined equilibria. Okay. Say sort of refinements might still give you sets, but okay. So notice sort of what's going to be interesting here then is sort of whether there exist equilibria that are informative about the dimension of interest. Okay, this could be either separating equilibria, or they could be partially pooling equilibria, and so on. Okay, so another useful observation is that in any equilibrium, the market belief function tau hat has to be non-decreasing along the path at least. Okay, so on the path of play, whenever a higher action is observed, the market belief has to be weakly higher. Okay. Why is that? Well, it's simply because higher actions have higher costs and agents want to generate higher beliefs. Okay, so it can't possibly be the case that you have two on-path actions where the higher one is generating a strictly lower belief, because then nobody would actually take the higher action. Okay. Okay, so these are observations that are useful, and one other sort of point before we jump into the analysis. So, what might one be interested in looking at in this kind of a framework? So one natural thing that one might be interested in looking at is welfare. Okay, so from the ex ante perspective, just take an expectation of the agent's utility. Okay, Another thing that one might be interested in looking at is something that you could think of as being allocative efficiency or expected gross benefit for the agent, which is simply from the ex ante perspective, forget about the cost, just look at the signaling benefit. Okay. We're going to do something related but different, okay, which is look at equilibrium information, okay, on the dimension of interest. So what do I mean by this? So clearly, if there existed a separating equilibrium on the dimension of interest, okay, and you should always keep that in mind. Sort of when I say separating equilibrium, I mean separating on that dimension. Okay, it may not reveal both dimensions of an agent's type, but the agent's type on the dimension that the market cares about is revealed. So that would clearly be a most informative equilibrium. Okay, least informative would be pooling. Okay, and then in between, in order to compare equilibria. One way in which one can do this is to use the canonical partial order of Blackwell. Okay, so I'll come back, as I'm not going to give a precise definition here because I can get through what I want to without giving a definition. I'll give a definition in the second lecture because it'll be more important there. Okay, but some of you would have seen this. If you haven't, roughly speaking, what a more informative equilibrium or more informative information corresponds to is a mean preserving spread off the distribution of posterior beliefs. Okay, so sort of flesh that out a little bit. Fix an equilibrium. Okay, from the ex ante perspective, that equilibrium generates some distribution over market beliefs on the dimension of interest. Okay, and you should keep in mind here that it's a distribution over distributions because whatever the dimension of interest is, okay. Whenever the agent takes some action, the market is going to have some distribution over the agent's type on the dimension of interest. Okay, so that's a distribution. From the ex ante perspective, the equilibrium is going to generate some stochastic process over that posterior distribution. Okay, so because there's two kinds. The agent may be mixing, and moreover, the type is being drawn stochastically. Okay, so. We could ask from the ex ante perspective, what is the distribution over the posterior distribution? Okay. And then if you have two equilibria, one of which has a mean preserving spread of this ex ante distribution off the posterior distribution, then we'll say that distribution is more informative. Okay, that's the Blackwell notion. Sort of minor aside, you might say, well, since what we care about is really not the entire posterior distribution, just the posterior expectation, why doesn't one try and generate a finer order? So this is going to be a partial order, okay, in general. Why doesn't one try and generate a finer order by looking only at the distribution of the posterior mean, since that's what's entering the agent's value function? Okay, one can do that too, and for a lot of what I have to say, it won't make much difference which one of the two you use. Okay, the two will be equivalent. Okay, but in general, this is going to be a finer order. Okay, and sort of what's the connection between why might you care about equilibrium information? Okay, so notice that if you fix stakes, so any given parameterization of the problem, whenever you have a convex value function v, okay, if you have a more informative equilibrium, that's going to correspond to more allocative efficiency. Okay, so this is a classical result. Okay, that whenever you have a mean preserving spread, you're increasing the expected value of a convex function. Okay. Conversely, this is what we were talking about earlier, V were linear, then the allocative efficiency is going to be independent of information. Of course, if it's concave, then you actually want to reduce information. Okay. Okay, so the words about literature. So sort of what I'm talking about is based upon some of my recent work with Alex Frankel. Okay. If you want to sort of connect this model with other things that you may have seen, so signaling with one-dimensional types, you could view that as being a special case of this model, where you've just fixed the type distribution of one dimension to be degenerate. Okay, so if you fix, for example, everyone to have a zero natural action, call it zero, doesn't matter, that's just normalization. So if you fix everyone to have the same natural action and you only have heterogeneity on gaming ability, that's the Spence model. Okay, so in Spence, basically you're trying to convince the market that you have a lower marginal cost of signaling. Okay, so that's gaming ability. You could do the flip side where you say, let's fix the gaming ability, okay, and instead only vary natural actions. Okay. This is work that I did, for example, in the context of strategic communication with lying costs. That's basically that problem where everybody sort of has some cost of misrepresenting information, and what you care about is sort of what is the true state of the world that this expert may be informed about. Okay. Or somewhat relatedly, it's not exactly the same. This is sort of Bernheim's conformity paper in the 90s. Okay. Or there's sort of literature in the accounting stuff about earnings management, which ties into this. There's sort of stuff on multidimensional signaling, and I've already alluded to this sort of work by Benabou and Tirole, and then Fisher and Verrecchia is basically related to a variant of this kind of a model. I'll come back to this if we have time. Okay, they, for example, don't have this free downward deviations business, and then there's some other stuff that happy to sort of once the slides are posted, you can find these papers and connect them. Okay, let me move on. Okay, so. So, you might say sort of, if what you're interested in is getting incomplete separation, why do a multidimensional model? Sort of, can't you do it in other ways? And the answer is yes, you can. There are reasons why this is still interesting. Okay. Here's the list of sort of possible ways in which you can do it. But let me move on. Okay. Okay, so let's jump into some details, some analysis here. Okay, so the kind of simplest case to think about that's going to give you a lot of the intuition about how the model works and sort of what's driving the information results is to think about the simplest interesting case. So what do I mean by that? If you had a model in which you could effectively collapse it back into one dimension because there are no cross types, so for instance this, then there's going to exist separating equilibria, okay, simply because there's single crossing in each dimension. Okay. So the simplest interesting model would be a two-type model where you exclude these guys. Okay, so you only have two cross types. Okay, so that's what I want to start out talking about. Okay, and just work through the mechanics here. Okay, so let's think about the case where the dimension of interest is the natural action. Okay. We've got two types, let me call them theta 1. I'll sometimes refer to this, just to make my verbiage easier, as the natural type. Okay, so this is a high natural action, low gaming ability, and theta 2, low natural action, high gaming ability. Okay, so this is theta 1, that's theta 2. Okay, so here's a little claim. There's some critical stakes level, S star, okay, such that there's a separating equilibrium if and only if stakes are lower than that critical level. Okay? And this should immediately contrast with standard models with single crossing. Okay? Okay, so this is easy to work through. So what's going on? So here's the cost curve picture that I had before. Okay, same thing depicted with just these two cross types. Okay, so think about the case where we start out with very small stakes. Okay, with very small stakes, there will be a separating equilibrium in which each type just plays its natural action. Okay, clearly the high natural action type, given the specification of behavior, is doing very well. It's not incurring any signaling cost, and it's getting the high belief. Okay, the gamer type, the one with the low natural action, will have to incur some discrete cost in order to move its action from its natural action to the other types. Okay, and if the stakes are sufficiently small, that's not going to be worth it. Okay, so there will be a separating equilibrium. So now we start increasing stakes. Keep increasing stakes for a while, that separating equilibrium is going to keep persisting. Okay, and then at some point, once the stakes get sufficiently large, the low natural action type, the gamer, is going to be willing to pay the cost in order to mimic the high natural action type in order to generate this higher belief, even though it bears some signaling cost because the stakes are not large enough. Okay, so you could do that. So then how do you get separation thereafter? Well, it's the standard kind of signaling mechanism at work. Okay, you at this point, sort of this high natural action type has to start distorting its behavior, okay, incurring a signaling cost in order to separate itself from the low type. Okay? And so you have this type start taking a higher and higher action in order to separate itself. Okay? So keep doing that for a while. Keep going, keep going, keep going, keep going, keep going, up until some point where we get to this cost equalizing action. When we get to the cost equalizing action, if we sort of can't go any further, because if we went any further, it's now the gamer type, the low natural action type, that has the lower total cost. Okay? So you can't possibly get separation by having the high type, the high natural action type, taking an action that's even higher. Okay? So it's as if endogenously, once the stakes get sufficiently large, this cost equalizing action acts like a barrier on the action space. Okay? And you can't get any further separation above this critical stakes level S star. So this critical stakes level S star is going to be defined at whatever stakes it is that ensures that if the high natural action type takes this cost equalizing action, the low natural action type is just indifferent between revealing itself at no cost and getting the high belief by taking the cost associated with this distortion. Okay, is that clear? Okay. Okay, so that's what's going to happen. And then at higher levels of stakes, there's not going to be a separating equilibrium. Okay. However, for no matter how large the stakes get, there's going to be partially informative equilibria in this problem. Okay, in this simple two-type case. So how? Here's a depiction of what's going on. So, and the key thing is the existence of this order reversing action that I talked about, the assumption about the cross types. Okay, so here's the low natural action. Here's the cost equalizing action. Okay, order reversing action. And suppose that stakes have gotten above that S star threshold. Okay, so there's no separating equilibrium. We can instead construct a partially informative equilibrium where both types are mixing over a pair of actions. Okay, and again, this is unlike standard models where the single crossing will ensure that you can't have both types mixing. Okay, so how do you do this? Perhaps the easiest one to think about actually is, let's take this A1 equal to eta lower bar and take A2 equal to the cost equalizing action. Okay, you can actually do it for a continuum of actions in between, but just think about pushing these to these extreme points here. If we do that, by definition of this cost equalizing action, the two types bear the same cost, okay, of taking this high action relative to that low action. Okay, and so the only thing is that we just need to generate the right amount. The beliefs have to be right at the two actions in order to get the gain, the signaling gain, to equal the signaling cost. Okay, how do we do that? Well, we just do that by getting the randomization appropriately. Okay, you have to get a higher belief at this action than at that action, since there's a cost associated with taking the higher action. And how do you get the higher belief? Well, you must have the higher type, the high natural action type, play this action with a higher probability than the low natural action type does. Okay, so, and obviously, sort of, you can get the mixing probabilities right in order to generate the appropriate beliefs. Okay. Yep.
So can you explain again why? I mean, I cannot see why in a standard signaling game where the actions are bounded from above, you can get partially cooling equilibria, but not both types. One type does not mix.
Correct.
In both types, can you just explain what is the difference between the models?
Yes, so that's a very important thing to be clear about. So in the standard model, you basically don't have this order reversing action. Okay, so in the standard model, at any action, okay, in a two-type specification, the higher type has a lower marginal cost than the low type. That's not true here. Okay, in particular, at the order reversing action, these two types have the same marginal cost. Above the order reversing action, it's the one with the higher gaming ability that has the lower marginal cost. Below the order reversing action, it's the one with the higher natural action that has the lower marginal cost. Okay, and that's sort of in the standard model, for example, this cost equalizing action just simply wouldn't exist. There would be no point at which the total costs are equal. Okay. Okay. Okay, so now here's another thing to notice. So what I've just argued is that no matter how large stakes get, there's going to be partially informative equilibria in this model. However, you can get a sense of a comparative static that we're after. Okay, so as stakes get large, the information must vanish in these partially informative equilibria. Okay, why? Well, suppose that so what do I mean by information must vanish? I mean that the market belief must equalize at these two actions. Okay.
So the mixing probabilities converge.
Yes. So why is that? Well, fix any difference in the market beliefs between these two actions. Okay, the two on-path actions. Well, as stakes get very large, the assumption was that the marginal benefit of generating the higher belief blows up. Okay. Since the costs are bounded, okay, because we fixed what this cost equalizing action is, okay, clearly that can't remain in equilibrium. And so the only way in which we can generate these equilibria as stakes blow up is to have the difference in the beliefs get arbitrarily close to zero. Okay. At the limit, it will be zero. And so that sort of should provide some intuition as to why it is that in the specification, as stakes get larger and larger, the market gets less and less information about natural actions. So there's going to be, so you should, this is just one example of an equilibrium. So there's lots of equilibria here. So as I said, you can support these equilibria where you have different actions. Okay, so it could be over here, because the key thing is that there will always exist a pair of actions. There's going to exist a continuum of pairs of actions around this order reversing action that equalize the difference in costs. So you can support the equilibrium with sort of any actions that are in between. And in fact, you could even go below this eta lower bar. So you can't say very much about exactly what the actions are. Besides, it can never be above the cost equalizing action.
I mean, the limits, the marginal benefit of higher belief is infinity, right?
But the belief difference is going to vanish between the two actions. So you could pick sort of, for instance, these two actions, or you could pick actions that are equal to these two, and you would just have to adjust the beliefs in a way that adjusts for the change in the costs. Okay. Yep. Uh-huh. So you're saying that the higher gamer would sort of separate himself? Yeah. No, that will never work, because as stakes get very large, notice that he doesn't want to reveal himself as being, so the assumption here is that we're looking at these types. So the higher gamer, this guy, has the lower natural action, and they care about the belief about the natural action. So he doesn't want to reveal that he has a low natural action. Yeah, so the preferences are monotonic. So even if it's slightly, he still prefers to generate the belief that he has a higher natural action. It may be small, so perhaps the confusion is that, so the assumption is that when stakes get very large, even this marginal difference, the marginal benefit blows up. Is that clear? Okay. Yes?
So, does the vanishing information mean that the posterior is the same as the prior?
Yes. So that's going to so the way I framed it was that the posteriors have to be equal, but then if you apply iterated expectations, they have to also then be equal to the prior. Okay. Yes.
So for this equilibrium, it's particularly important that you can separate the belief from the two types. So tau hat from tau in the references.
No, this is a two-type case. So I could use any statistic of the beliefs is going to be summarized here by just the expectation, because there's only two types. Okay, so with more than 2 types, they're not equivalent. Okay, 2 types they are. Okay, so so summary sort of, what we've suggested, obviously not proved, is that at any stakes there's going to be some informative equilibrium, more or less proved that. Higher stakes equilibria are less informative, sort of suggested that. So how does one go about trying to prove this a little bit more rigorously? Here's the way in which the argument goes, and this is still just going to be a sketch. Okay, so the idea is that we want to basically prove a perturbation argument. Okay, so let me explain what I mean. So take an arbitrary equilibrium. Okay, what we want to show is that when stakes reduce, okay, we can construct a more informative equilibrium. Okay, so pictorially, so think about stakes on the horizontal axis and some measure of information. Let me just be vague about exactly what it is on the vertical axis. Okay, so what I want to show, we want to capture the idea that when stakes increase, information reduces. Okay, in some sense that I will make precise. Okay, in an appropriate set order sense. But intuitively, one way to do that is you say take some equilibrium at some level of stakes. S upper bar, let's say, and then show that when we lower stakes, we can actually find an equilibrium that has more information. Okay, so that sort of, if you then think about either, for instance, let's say the upper envelope of the set of equilibria, this is going to imply that it looks like a decreasing curve. Okay, that's the idea. So how does one go about doing that? Look at the particular equilibrium we were thinking about before. Okay. We start out with some equilibrium where we've got these 2 actions, both types are mixing, and that's what I've depicted here, where we've got both types playing both actions. Okay. Lower stakes. Okay. When we've lowered stakes, if we don't change the equilibrium, if we don't change behavior, the previous behavior will no longer constitute an equilibrium. Okay. Why? Because they were indifferent before. And there's a higher market belief here than here. We just lowered stakes, so agents are no longer willing to bear the same cost in order to generate that higher market belief. Okay, so what do you have to do? Well, when you've lowered stakes, you've got to sort of increase the market belief over here and or reduce the market belief over here in order to increase the spread in the market beliefs to compensate for the reduced stakes. Okay, because we want to construct it using the same actions in this example so that we don't change the costs, we just have to play with the beliefs in order to change the values, okay, the benefits. Okay, so what do? Well, let's move some of these natural types, the high natural action types, to the right, and or move some of these high gaming ability types to the left. Okay. Since the dimension of interest is the natural action, that's going to increase the market belief here and or reduce the market belief here. Small change in stakes, we can do this if they were both types are playing both actions with positive probability. Small perturbation in the stakes, we can perturb the equilibrium in this way in order to generate a new equilibrium where we've spread the market beliefs and we spread it in exactly the right way that generates a mean preserving spread of the beliefs, right? Because we've just moved we've increased the beliefs here and reduced the beliefs here. That's a mean preserving spread. Okay. Now there's sort of a bunch of subtleties that one has to worry about, because when I made that argument, I was only looking at sort of the incentive constraints with these 2 actions, but one has to worry about other non-local, if you like, incentive constraints. Okay, so in particular, when we lowered the stakes, if originally a type was just indifferent, the low natural action type was just indifferent between taking this action and actually deviating off path to its natural action. Okay, because it had it was generating some intermediate market belief over here. It could just incur no signaling cost, go down to its lowest natural action, to its natural action. And the worst belief that it could get is that it really is this eta lower bar type, eta lower bar, gamma upper bar. Okay. And if it was originally indifferent, when we've lowered the stakes, it may now prefer to just engage in that deviation. So one has to sort of worry about other kinds of incentive constraints. And let me just explain this one thing, and this may be the last detail that I'll go through carefully. So how do we do this? If this incentive constraint were in fact binding, okay, what do we do? Well, so forget about this up arrow for a second. Just look at this horizontal arrow. Okay, so what do? We sort of first move some of this gaming type, the low natural action, high gaming ability. We move it down to its natural action if necessary. Okay, so if it were originally indifferent, we just lowered stakes. Okay, this made it now more attractive to take this action. So we just move some mass of these types down here in order to recover indifference between this action and its natural action. Right, you can do that because when you've moved some of this type over here, you've increased the belief associated with this action. Okay, so again, you've spread the belief over here. So you do that, and then the second step of the perturbation now, instead of doing this kind of a perturbation, you now take this high action and move some of the gaming ability type from the highest possible action all the way down to the bottom. Okay. Why does that work? Well, when you do that, notice that you're not actually affecting the market belief over here because the market belief is eta lower bar, and that's exactly the type that you're moving down. Okay. And you're not affecting the market belief over here, so that's key. And you've increased the market belief over here in a way that allows you to recover the same indifference that we wanted between this action and this action. Okay, and that will work. Okay. And notice, by the way, that's still the mean preserving spread. So even though we've now introduced we've changed the support. Previously we had just this binary support. Now we've got this triple support. But you've still generated a mean preserving spread because what you've done is you've moved the low type, the low natural action type to the left, and nothing else. Okay, so that's still a mean preserving spread. So that's still increasing information in the Blackwell sense. Okay. Yes. Yeah. So I'm going to show you. Okay. Okay. Okay, so summary, when the dimension of interest is the natural action, you get separation at low stakes and information decreasing in stakes. Okay, so let's think quickly about what happens in the other case. So suppose now the dimension of interest is the gaming ability. Okay, so now essentially the idea is that things are just going to get flipped. Okay, not exactly, but approximately. Okay, so here's one claim. Which is the analog of the first claim I had. So remember, with the natural action, we said that there was some upper bound S star such that you only get separation at low stakes and not at high stakes. Now, we're going to say that you only get separation at high stakes and not at low stakes. Okay, when the dimension of interest is the gaming ability. More precisely, there's not going to be these two thresholds. Okay, and of course, this S star doesn't need to be the previous S star. Bad notation. So there's going to be two thresholds: some high threshold and some lower threshold, okay, such that there's a separating equilibrium only if stakes are above the high threshold, and only pooling equilibria, uninformative equilibria, when stakes are below the low threshold. Okay, and I didn't state it on here, but there's going to be partial pooling in between. Okay, so why is this? Again, you can see this quite easily. Same kind of picture, these cost curves for the two types. Suppose that stakes are extremely large. Okay. When stakes are extremely large, you can basically have the gamer type, okay, just take an extremely high action. And because once the actions get sufficiently high, the red curve is below the blue curve, the gamer type has the lower marginal cost, it can just take a sufficiently high action in order to deter the natural type from mimicking it. So clearly, once stakes get sufficiently large, and remember, now it wants to reveal itself because the dimension of interest is the gaming ability. So once stakes get sufficiently large, we can just construct a separating equilibrium like that. On the other hand, when stakes are very, very small, if you like, think about close to zero, okay, you can't get any information being revealed. Why is that? It's again the same idea that this the sort of the discrete difference between these two types. Okay, so when the stakes are extremely small, the low natural action type or the gamer type is not going to be willing to sort of pay the cost associated with taking any action above 8 alpha bar, okay, because it's a discrete cost. Okay. On the other hand, for any action below 8 alpha bar, what is now the low type, this high natural action, low gaming ability type, can just mimic the other type for free. So you can't possibly get any separation, any amount of any partial information revelation. Okay, so only pooling equilibria exist. Okay, and the kind of general result that one can show again here is that as we increase stakes, equilibria become more informative now. Okay, and let me not go through the argument. It's the same kind of thing as we were doing before. Okay. Okay, so summary, when the dimension of interest is the gaming ability, we get separation at high stakes, pooling at low stakes, and you get information now increasing in stakes as opposed to decreasing in the other case. Yes. Say that again. It doesn't have to be. Doesn't have to be. So, I mean, here's the trivial observation. You can also pool at lower actions.
Oh, yeah, but it's
Okay.
higher than.
You could have pooling at higher actions as well. So, why? Because, so take some positive level of stakes that's very small. Okay. If we could generate pooling at just a slightly higher action than 8 at lower bar, supported by the off-path beliefs, because when they're pooling, you hold a prior. Okay. Supported by the off-path belief that if you take a lower action, you're going to be thought to be the low gaming ability type. Okay. Yes.
Give some example for why the market would be interested in the gaming ability and not the model?
Yes. So here's one. So think about sort of go back to the SAT example. Okay. It's a bit like I'm pulling a rabbit out of a hole now. So I tried to convince you earlier that what you care about is the natural action there. Okay. But I could tell a slightly different story, which is that it's not the way in which you improve your score for the SAT is not by sort of studying specifically for the SAT. It's rather by studying more generally. Okay, and now we might care about sort of knowing about, well, are you somebody who finds it, are you hardworking? Are you somebody who's able to pick up material easily? And that's something that we care about. Okay, so that's one story. I can tell again. Maybe the easiest way to justify this is that's Spence. Spence is the case where the market cares about gaming ability. Okay. Yeah.
Using when using master off-path techniques that when you get from higher action, the market thinks of you as if you have lower natural ability.
It doesn't have to be lower. You can always make it constant, right? Because nobody, if we just said that whenever you take a higher off-path action, we hold the same belief as the highest belief on path, nobody would strictly want to do that anyway. Okay. Yeah. So let me hold off on the refinements issue. So I can talk about this after class, but it can be reasonable is the short answer. There are cases in which it will not survive some refinements, like strategic stability-based refinements, like D1 and so on. Okay, but there are cases in which it will. Okay, so sort of 10 minutes. I'm sort of just going to now sketch sort of some more general results. Okay, so the point here is that what I try to convey is the intuition from this two types analysis. Okay, but obviously that setting is artificial. Okay. What you want to be thinking about is type spaces that embed cross types and ordered types. Okay, and there's basically three sets of analytical. The multidimensional signaling models are, and especially if one wants to sort of not take a stance on particular equilibria, they're generally rather intractable. So there are three sets of results that can be generated here. Okay, so one is sort of to look at the minimal such type space, which is a 2x2 type space. Okay, so these four types. Okay, and here one can recover exact comparative statics that we're interested in, namely information on natural actions decreases in stakes, information on gaming ability increases in stakes. Okay, and I'll state the result without saying much more than, because the proof is sort of along the lines of what we were doing before. Then one can sort of look at more general type spaces, and here sort of the way in which one can recover the intuition is to look at limits. Okay, so here basically we can look at limiting cases as stakes get very small, as stakes get very large, and the idea will be to show that if what you're interested in is the natural action, then as stakes vanish, you get lots of information. As stakes blow up, you get very little information. Okay. On the other hand, if what you're interested in is gaming ability, as stakes vanish, you get very little information. As stakes blow up, you get lots of information. Okay. And then there's sort of this this variation of the model that links it up with Benabou and Tirole and others, which is a very particular specification of the problem that's very conducive for actually working out what equilibria look like. Okay, so this is referred to as a linear quadratic normal specification. So what is this? This is the case where the market, the agent's benefit function just takes the form S times tau hat. So somebody asked earlier about whether the little v function can be linear. So that's in fact the case there. Okay, the cost function is quadratic. Okay. Okay. And let's stick the gamma here. Okay. And then the type distribution is bivariate normal. Okay. So that's this case. And here, sort of as is often the case with normal distributions and quadratic functions, one can actually explicitly solve for linear equilibria. Okay. And then you can sort of you recover exactly the same kind of comparative statics globally, and one can do some additional stuff like look at things like correlations and so on. Okay. Okay. So I'm just going to sketch what the results are. When thinking about sort of how to compare information across equilibria here, there are two issues. So one of them is already said is that sort of the Blackwell information measure is a partial order. Okay, so it may be that for any given particular level of stakes, there's multiple equilibria, and you can't actually rank them in terms of information. Okay, so that's one issue. But there's sort of another issue, which is sort of, even if you could for any particular level of stakes rank the equilibria, how do you now compare, there may be multiple equilibria, there generally will be, how do you compare the equilibrium set for one level of stakes with an equilibrium set for another level of stakes? Okay, there are standard ways there are standard orders that one could try to look at for comparisons of sets, and here's one. Okay, so the way in which to do it is to compare equilibrium sets using the weak set order. Okay, that's induced by the Blackwell partial order. Okay, so what do I mean? We're going to say that an equilibrium set A is more informative than an equilibrium set B. Okay, if two things are true. First, for every equilibrium in the more informative set, okay, you can find some equilibrium in the less informative set that's actually less informative, okay, according to the Blackwell partial order. Okay, and secondly, to the flip side, you take any equilibrium in the less informative set, you can find an equilibrium in the more informative set that is in fact more informative according to the Blackwell partial order. Okay, so this is sort of the weak order, the weak set order comparison using the Blackwell order for comparing points within these sets. Okay, is that clear? And as the name suggests, this is a coarser order than looking. So it's a weaker order than using the stronger set order that you may have seen in other places. Okay, so life is helped here because of free downward deviations. Okay, so why this first point becomes very easy. Okay, because when we're looking at the entire set of equilibria at a particular level of stakes, okay, both these sets are always going to contain pooling equilibria. Okay, since those always exist. So it's always going to be this case that there's one equilibrium in this less informative set that's less informative than the one in the more informative set, simply because both sets contain the pooling equilibrium. Okay, so this first point here is going to be vacuously or trivially satisfied. So it's really about the second point, okay, which is now should be ringing bells about why I was doing that kind of perturbation argument earlier. Okay, it's really basically about showing that in the more informative set, you can find one equilibrium that's more informative than whatever equilibrium you started out with in the less informative set. Okay. Okay. So here's the theorem. So take the 2x2 model and take any two stakes levels, low stakes and high stakes. Okay. If the dimension of interest is the natural action, then the set of equilibria under the low stakes is more informative than the set of equilibria under the high stakes. Okay. Or to say this another way, when you increase stakes, the set of equilibria becomes less informative. Okay. In the weak set order sense. Conversely, if the dimension of interest is the gaming ability, then the set of equilibria under the low stakes is less informative. Okay, or set of equilibria in the more higher stakes is more informative. Okay, so and the proof basically extends what we were talking about before. Okay, these kind of perturbation arguments. Okay, so that's the 2x2 questions. Okay, so quickly the general case. So consider an arbitrary type space capital theta, okay, compact, and let's denote the projection of that onto one dimension as just theta subscript that dimension. Okay, in particular here theta sub eta. Okay, so if the dimension of interest is the natural action, okay, and suppose that there's a finite number of natural action types, okay, then for sufficiently small stakes there exists a separating equilibrium, okay, on the dimension of interest, which is the natural action. Okay. And the proof of this is fairly simple. It's simply observing that given that there's a finite number of these natural action types, when stakes are really small, every type can just play its natural action. There's a finite number of these natural action levels, and so there's going to be a discrete cost of any type of mimicking a higher natural action, and if the stakes are sufficiently small, that's not going to be worth it. Okay, so that's easy. The second is that so long as the type space contains at least one pair of cross types, okay, then for sufficiently high stakes, there can't be separation on the dimension of interest. Okay, the natural action. Okay. And clearly, if the type space does not contain a pair of cross types, then no matter what the stakes level, as long as they're sufficiently large, there is going to be separation. There will exist equilibria in which there is separation. Okay, because they're going to be ordered by single crossing. Okay. Okay. So.
Can you say anything about the partial separating, partial pooling equilibria?
I will in a second about limits.
Okay.
But only about limits.
Okay.
Okay. So here it is. So this assumption is a little bit stronger than we need, but it makes the statement easier. So suppose that the types are distributed independently across the two dimensions. Okay. And the marginal on the gaming ability is continuous. Okay. Then as stakes blow up, all equilibria become uninformative about natural actions. Okay, so there may exist these partial pooling equilibria.
Do you know whether they exist for large values of S? Or you might just get a pure pooling equilibrium for all. I mean, this proposition doesn't distinguish between that.
True. So I don't have a precise statement off the cuff, but you would morally expect that they exist, and we know in examples that they do. So we saw that example previously. So if we look at the 2x2, for instance, they will. I don't have a precise statement. So okay, I'm out of time. So you sort of you can allow for some generalizations. You don't quite need independence and so on. Okay, and so let me end by just taking 2 minutes and just state the results for the other case, and I won't have time to talk about the linear quadratic normal. Happy to talk about it offline. Okay, so it's essentially just the flip sides, what you would expect. So now think about the case where the market cares about gaming ability. Okay, if you've got a finite number of the gaming ability types, then for large enough stakes, there's going to be a separating equilibrium on gaming ability. And as long as there's at least one pair of cross types, then for sufficiently small stakes, you can't get separation. Okay. Moreover, if you have independent distributions, or the distribution is independent of the two dimensions, and you have a continuous marginal on the other dimension, on eta now, then as stakes vanish, all equilibria are going to become uninformative. Okay. And leave the proof as a homework exercise. Okay. Johannes, question? No. Okay. Okay. So let me end there, unless there are other questions. Yes.
If we go with the other intuition that's been said here, that with higher stakes, it's more costly to conceal your pure type. So it's exactly the other way.
Yeah, so that's a good point, right? So the intuition here should suggest, ultimately, sort of the intuition that I'm trying to convey is that sort of, what's going to matter is whatever dimension it is that's ordering these marginal costs. Okay, as stakes get really large, everybody's going to be distorting their actions a lot. Okay, and so whatever it is at high levels of actions that's ordering the marginal cost, that's the dimension about which you could extract information. Okay, so in the specification here, when everybody starts distorting their actions by a lot, it's by assumption it's the gaming ability that's affecting the marginal cost, that's determining the ordering of the marginal cost, and so that's the dimension when stakes are very high that you can get information about, and you can't get information about the other dimension. Okay, if instead you assume that when everybody starts studying, when everybody is spending hours and hours practicing for music, okay. What sort of determines their marginal costs or their benefits is their true innate abilities, then that's what you're going to get information about at the limit. Okay. Okay, thanks.